So yeah, Jinpeng Wei again. So I'm an associate professor at the UNC Charlotte, and so working on cybersecurity. So today is my honor to be in the CAE forum to talk about my recent project, and that is ShadowMove, a Stealthy lateral movement strategy. So the technical background of this project is advanced persistent threats, or APTs. So APTs are sophisticated, well-planned, and multi-step cyber attacks that pose serious threats for the security of mission-critical enterprise systems. So one famous APT attack is the Equifax breach, which revealed the personal data of millions of users. So this APT attack starts with a compromise of the Equifax dispute portal server because that server suffers from one vulnerability. So once the attacker landed on the portal server, so he or she discovered the saved login credentials. And then using those login credentials, the attacker is able to enter the database server of Equifax. And then on that server, the attacker discovered a huge amount of personal data, and then it's filtered outside. So this example illustrates the lateral movement aspect of the APT attacks. So basically, after the attacker established a foothold, within the targeting system, so the attacker used the compromised systems as the stepping stone to reach further systems, and then until they can reach to the critical assets, for example, the personal data in this case. Okay, so then how does the APT attackers make the lateral movement? So that's the research question, right? So basically, once they compromise one node, how can they systematically lateral move into other systems, and then until they can reach their critical assets? So let's first review the known state of art for the lateral movement. So there are three techniques. The first technique is vulnerability exploitation. So here the idea is to exploit a vulnerability that is known and unpatched. And then by doing that, then the attacker can move to the vulnerable server, for example. So there's some limitations for this idea. So first, the server must have some vulnerability, and they must not be patched yet. Right? So not every server suffers from a vulnerability. And second, the exploitation are also kind of easy to detect because this exploitation violates the integrity of the server. So there are techniques that can detect that. Okay, the second known technique for the lateral movement is credential abuse. So the idea is to harvest and then abuse the credentials to enter further systems. So the idea is very straightforward, right? So they first collect the user logon, username, passwords, and then just use those information to enter more systems. And so this also suffers from some limitations. So the credentials are not always easy to get. Maybe they are not saved, or they are saved but encrypted, for example. And also credential alone may not be enough for the lateral movement. If we know that now the two-factor authentication is deployed widely. And the third, that abusing these credentials to then enter another system actually requires a new network connections to be made. And this actually can be picked up by the IDS as anomaly. Okay, so then the third kind of lateral movement technique is process injection. The idea is to inject the application and protocol specific code into the legitimate clients so that to reuse or abuse its connections. So here the starting point is that the legitimate client is already connected to the legitimate server. It already finished the authentication, and then there's already a connection. So now this idea will inject the code into the client process. As a result, that code can just enjoy or access that connection that is already established. And then through that, finish the lateral movement. So this technique also has some limitations. First, it is very complex and it's very hard to implement because how to guarantee the code will run properly inside another process, So this requires some knowledge, right? For example, of where's the location of the socket variable and so on in that foreign process. So this actually requires a lot of reverse engineering and a lot of effort. So it's hard to get it right. And also, this also is kind of easy to detect because it violates the integrity of the client program. So it's also not very serious. Okay, so given the understanding of the existing state of art, we discover a novel lateral movement technique that we call ShadowMove. So our idea is to silently reuse existing and legitimate network connections to do that lateral movement, but we do not rely on process injection. Okay, so our idea actually is using socket duplication, which I will talk about on the next slide. But here I just want to give you a high-level idea of how this actually works. So suppose that we have a enterprise employee self-service application, right? So this involves a web server, application server, and then the database server background, and then this service can be accessed from any client machines using web browser. Okay. So suppose that one of the employee is also IT admin, right? So this admin also need to manage the app server. So for example, upload the new code and upload the data and so on. So as a result, this two machine, the administrator machine also is running FTP, this application to copy files, and also the Windows remote managed WinRM application to remotely launch script, for example. Okay, suppose this is a setting, and now this malware APT compromise the IT personnel's machine, right? So then this suppose that the legitimate IT personnel already opened the FTP application and the WinRM application. Suppose those applications are already running, so that those connections are already there, right? So then this malware can abuse the FTP that connection or copy itself onto the application server. The first step, and then you use the Windows RM that connection to start its execution on the application server. Okay. And then once this malware runs on the application server, so this is finish one step lateral movement, right, to the application server. Then this attacker will discover MS SQL connection, right, to the database server. So then again, by abusing this SQL connection, the malware can copy it itself and also launch it itself on the database server. And then this is overall how the ShadowMove can help. So we call this ShadowMove because you can see it's running under the shadow of existing connections, right? So those connections, FTP, SQL, they are already established. They are already working. So now we just sneak into inside these connections. So that's why we call this ShadowMove. Okay, so then let's look at the more technical details. So how we do it? So from a single hop, move. So this is our basic idea. So suppose that we already have the client machine that is connected to a server machine, right? And then the attacker compromise the client machine. So then the first step is to duplicate the socket that is used by the client to talk to the server. You get a duplicate of the client socket. And then through that duplicate socket, the attacker process can inject malicious payload into that existing connection. And then when this a malicious payload is handled by the server. So the server doesn't know these are actually malicious payloads. So the server just will process them as usual. But the effect of those is actually server may inadvertently saves and or launches another instance of the shadow move. So as a result, this one-step movement is finished. Okay, so this is an illustration of how this can be done over the FTP protocol. FTP. So suppose now that we have an FTP client running. So initially, so it creates a socket and then connect to the FTP server and then exchange some packets for the authentication. You can see these are the normal exchanges. So now the ShadowMove starts to run on the FTP client machine. Right? So first, it get a duplicate the client socket, duplicate socket. So that duplicated socket will allow the ShadowMove process to inject the packets into the same connection to the FTP server. So then the next, before doing that, first this malicious process suspend the FTP client, so to avoid any interference, right? So after that, it starts to inject packets in order to upload the malware itself to the FTP server, just using the regular FTP command. So for example, the CWD command is changing the working directory, right? So then the server just respond and normally say, okay, the directory is successfully changed. And then the malware send further packets to switch to the binary mode, and then to the passive mode, and then to upload the malware. Okay, so the effect of these several packet exchanges is eventually a copy of the malware is uploaded onto the FTP server. So eventually, then after this is done, the malware just resume the normal FTP client's execution. Okay, so that's the illustration of how the ShadowMove works in just one single hop, right? One single hop. But in a real network, right, this may not be sufficient because maybe the valuable targets are multiple hops away, right? So only one single hop is not enough. So therefore, ShadowMove will need to continue to search and move towards the target. So what we do is the ShadowMove will systematically learn a global network view of the target network by leveraging the already discovered and abused connections. And then this network view is basically a graph. Okay, the nodes represent the hosts. Right? The edges represent the connections among the hosts. Okay, and including, for example, what kind of protocols are running there. So then this as the APT make a progress, and this graph is kind of gradually learned and gradually enhanced. Okay, so for example here, then they discover a new node with the IP address ending in 100. Okay, later, and through a FTP connection. Okay, okay. So then, but here this through by abusing this FTP and so on, the attacker is only able to copy itself onto the target machine, but not able to run it because the FTP protocol doesn't allow the remote kind of launching kind of capability. So therefore, this attacker will try to see, okay, discover there's another connection, another path from the initial foothold, and then continue this discovery and eventually discover a Windows RM connection to the same target host. So then now with all this together, right? So the attacker is able to finally launch their malware on a target machine. So this is the global network level illustration how the ShadowMove works. Okay, so then I'm going to just look at talk about before I go into technical details, I just want to talk about what is the strength or the advantage of ShadowMove over the traditional LateralMovement attack techniques. So basically, ShadowMove is a more general and scalable solution, so therefore it is more powerful. So in more detail, the traditional lateral movement techniques, they are application specific. So as a result, they are not very scalable. For example, the vulnerability exploitation requires, there must be an unpatched vulnerability, but that vulnerability only occurs in one particular server, right? On one particular version of the server software. So it's always going to be case by case, server specific. So the attacker cannot develop one powerful tool that will work across all servers. So that's why it's not scalable. The credential abuse is the same, right? So each stolen collected credential only works on one particular server, right? So it cannot, the same username password may not work on other servers, right? So again, it's not very scalable. Okay, but the ShadowMove is different. It's more general. So basically, it works for any server and any client, because the ShadowMove is based on protocols instead of applications. Okay, so for example, there are almost 100 different FTP clients and FTP servers available. Right? So the different tools, there are so many different tools that is using the FTP protocol. So however, a ShadowMove only need to develop one thing for the FTP protocol. So this is one thing will work across all the different clients and the server software. So therefore, ShadowMove is more scalable and more general. And also in today's enterprise environment, ShadowMove has plenty of opportunities to cause damage. So first, there are a large number of protocols that have public specifications, right? For example, FTP and so on. So because they are public, right, those protocols, they are public, so the attacker has enough time to study those protocols, find how to abuse them, how to inject a packet and so on, and then build the attack tools. And also there's a wider spread of automation and also the weaker protection inside the environments. So for example, passwordless SSH login, and then the people don't use encryption inside the enterprise, right? Because they think in the enterprise, inside the network, every node should trust each other. So there's no need to do encryption, decryption, because people want to have higher performance, right? But then all these actually make it easier for ShadowMove. Okay, so then the threat model of the ShadowMove is that we make several assumptions. So first, this hacker, they has already established a foothold on a victim system under a normal user privilege. So basically, ShadowMove doesn't need a root user privilege. Okay. And then this assumption is very easy to satisfy, because spear phishing, drivable downloads, they are very popular attack vectors. And then second assumption is that attacker, they run malware to automatically move towards the assets. And the third assumption is that the victim process, whose the TCP connection is going to be hijacked, is not aware of the malware process. So for example, that FTP client is not aware of any attack process running side by side with itself. So this is our threat mode. Okay, so I'm going to talk about the design of a ShadowMove. So this is so you can see this architecture. We have multiple components. So we have the network view manager in the center, right? So that's the component that learns and manages and maintains the global network view that I introduced. And then two components that are supported this is the socket duplicator, the duplicator socket, and also the connection detector and the peer handler, so which I will describe on the next slide. And then we also have a lateral movement planner, which will make an action plan based on the current network view, right? And then in terms of what to do next. And then these actions are carried out by the actuators. Okay, so a little detail about the connection detector. So this is a component that detects the new created socket that is suitable for duplication. Okay. So the idea is straightforward. So it periodically get the list of TCP connections, and then in order to discover the new connections, right? And then it try to recognize the what kind of protocol, right? And then and also it pick those protocols, and then filter out some of the connections that are owned by the privileged processes, because remember that ShadowMove just runs as under normal user privilege. So as a result, it cannot duplicate the socket that is owned by the privileged process. So do some filtering. So then only then after that, call the socket duplicator to duplicate the sockets. So here is some information about how the socket duplication works. So let's first review how the socket duplication is done in a conventional way, in a traditional way. So basically, today's operating systems, they support socket duplication for a good reason. Okay. However, the traditional duplication, they requires the cooperation between the socket owner and the other process that try to share the socket. So here is the example based on Windows platform. It takes multiple steps for this socket duplication. So first, the owner process will create a socket and then make the connection by calling this WSA socket and WSA connect, right? And then suppose that the socket is usable, and then the owner process want to share it or transfer it to a partner process. So before doing that, first the owner process ask their partner process for its process ID through IPC or inter-process communication, IPC mechanism. So then the partner process answers the ID, and then after that, the owner process call the WSA duplicate socket to create a second socket, and then pass it along to the partner process in a data structure called the WSA protocol info. This data structure again through the IPC mechanism to the partner process. So after the partner process receive this data structure, it uses it to call WSA socket. So then it can kind of reproduce a socket, which is the duplicate of the original socket. And then it can use this duplicate socket to send the receive and so on. In the meantime, the owner process can just close its own socket. So this will finish the kind of the duplicate of the socket, right? From the owner process to the partner process. So this is in today's operating system in Windows, how this is done. But we can see that this requires the cooperation, right, between these two processes. Okay, so ShadowMove cannot use this idea because ShadowMove is an attacker, right? So it doesn't want the victim process to know that he's this malware is trying to steal the socket. So instead, the ShadowMove has a novel idea that invokes the relevant Windows APIs, but in an unconventional way. Okay, so as a result, it doesn't require any cooperation from the socket owner process. Okay, so this table shows some detailed steps of what happens or how to do that. So basically, initially, the malware process has to open the owner process with the process dupe handle privilege, then get a handle to the owner process, and then as a result, it can enumerate and duplicate all the handles inside of the owner process, and then it does some filtering to just find the handle that corresponds to the socket. Okay, so this is the step 2 to all the way to step 7. So basically, do some just to recognize which handle is the socket. Okay. After that, this malware can just call WSA duplicate socket itself on that using the handle, and then followed by to get the WS protocol info structure, and then invoke WSA socket W on itself, and then to get a functional socket. After that, then you can use the receive send as normal. Okay, so these kind of by following these steps, then this malware process doesn't require the cooperation from the target or the victim process. Okay, so then this is about socket duplication. So now I'm going to talk about another component, the peer handler. So this is the component that helps to construct the global view of the compromised network. So basically, there is the peer handler is running on every compromised host, and then these peer handlers they can they cooperative talk to each other, and then to exchange and merge their local views so they can collectively construct a global view. That's the basic idea. So therefore, this peer handler on one hand will receive the network views from its neighbors, right? Again, from the abused network connection through the duplicated socket. And then this is on one hand, receive the views. On the other hand, it also send its own local view to the neighbors. Okay, so this is the way that the this ShadowMove instances that they can collectively learn the global network view. Okay, so then the next component is the lateral movement planner. Lateral movement, planner. Okay, so basically this component would create the next lateral movement action plan. So based on the current network view, right? So and also what has been done, the history of the actions that has been done during this APT attack process. So this planner try to optimize for the most effective and the steals. So it can choose for example, the shortest path towards that valuable target and so on. And it is based on logical programming to make this kind of create this kind of plan. And then here this each action plan basically describe the exact action that must be performed on a particular compromised node. Okay, so this is a little more detail about the lateral movement planner. So it maintains a set of logical programming predicates. So some of the predicates are derived from the knowledge, about the capabilities of protocols. For example, FTP can upload files, can download files. The WinRM can execute, right? Can remotely execute something. And then another set of predicates is actually derived from the global network view. And you can see that some predicates represent the connection between the nodes and the kind of protocols that are running inside the connection. Other predicates represent the actions that are already committed, right? So for example, here, this means that the upload of some file is already done, okay? And then this is a set of predicates. And then we have the logical programming rules. So these rules are defined that help the planner to find a path, right, to reach the target. So then using these rules and the predicates, and then they just do reasoning a lot, and then do logical programming, and then eventually find the right action. So for example, given this in this particular case, and then the result is that okay, we should use the WinRM connection. This is leverage this connection to launch the malware on the target. Okay, so then the last component, they are the lateral movement plan actuators. So these actuators, they are protocol specific, right? So they know how to create the protocol specific queries or the payloads in order to carry out some actions. So for example, how to utilize FTP protocol for copy malware, right? So then how should that packet look like? So these kind of actuators actually will create the packets that is following the protocol, and then with the right parameters inside. So as a result, to finish some actions, right? So file copy files is one action. Another kind of action is how to remotely execute, right, a file on the remote server. So this is about the actuators. Okay, so then we implemented this idea, the ShadowMove architecture. So in the more than 2,000 lines of C++ code on Windows, the latest Windows 10, and we also have a prototype for the Ubuntu. And then the lateral movement planner is based on the SWI prolog. So we use the prolog for the logical programming part. And then we build the 3 actuators. They know how to abuse FTP, the Microsoft SQL, and the WinRM, those protocols. Okay, so this is another kind of illustration of how the ShadowMove can abuse the WinRM. this connection. So we build a prototype that works. So basically, this can remotely launch the malware on another system. Okay. So then, similar to the FTP example, right? So we have the WinRM client, which is connected and talking to the WinRM server, right? And then this WinRM client machine is compromised. Okay. So we can also see the exchange of that packets. The first part is the client send the authentication request, and then the server answer the response to with the shell ID. This is the one ID generated by the server. And then the client follow up with a request that use the shell ID, and then but add the message ID and the actual command, right, to run on the server. And then the server will send back the command response. So here the command can be just a command line, right? So what happens that here the ShadowMove malware will first duplicate the client socket, and then it can actually listen or peek as into that connection. So as a result, it can overhear this shell ID from the server. So when the server sends back the shell ID, so then this packet not only reach the legitimate client, but also it is picked up by the ShadowMove. So therefore, the ShadowMove malware also knows about the shell ID. So using this ID later, the ShadowMove can fabricate the malicious request, and then with the legitimate shell ID, but then with other attack commands and so on, and then send to the remote server. So this is an illustration of another protocol that we implemented. Okay, so why so let's talk about the evaluation, right? So how effective is this, and also more fundamentally, why ShadowMove attacks are possible. So we think there are two fundamental reasons for this. First one is the conflicting requirements between process isolation and the resource sharing in a modern operating system. So both the current operating system, right, supports process isolation, for security and so on, but they also support resource sharing, because resource sharing can be useful, right, for certain application scenarios. But then you can see that these two kind of requirements, they actually are conflicting, right? Because process isolation, resource sharing, of course, will allow the processes to talk to each other and then share something in common, which is against the isolation. Okay. So because today's OS must support both, so then the ShadowMove actually take advantage of the sharing part, more specifically, right, socket sharing part. So basically, it can abuse the socket sharing support by the operating system, so that some of the sharing actually are malicious. Okay. The second fundamental reason is a lack of the built-in message origin integrity validation in many networking protocols. Okay, so this is origin integrity is about how to prove that the request is coming from a legitimate client, right? Because in the ShadowMove case, so basically the ShadowMove, the malicious process actually send some malicious request packet, but inside the legitimate connection, right? So then when this kind of a malicious request packet is received by the server has no way to tell the difference, from this maliciously constructed request packet and those benign legitimate request packet. So the server has no way to tell. So that's why the server will go ahead and then actually act upon them. So that's the second fundamental reason that enable the ShadowMove attacks. Okay, so then we look at the stealthiness of our proof of concepts. So basically, we have three proof of concepts, right, based on the FTP and the MS SQL and the WinRM. And then we run them, and then while we deploy 5 antivirus and 1 network IDS, 3 host-based IDS, and 2 EDR, enterprise data detection and response systems. So basically, we use these state-of-art defense mechanisms, or those tools, to see if they can detect our proof of concepts. So the result is is that none of them was able to detect our proof of concepts. Okay, so the current our prototype do have some limitations that very briefly. So first, it cannot hijack the connections for which they use the user level encryption. Okay, so basically, if these protocols they apply the encryption, and then the ShadowMove cannot hijack and abuse those connections because it doesn't know the keys, right, to create the malicious packets. And the second limitation is that it may not be able to get those critical information such as the shell ID, right, in a WinRM attack, right? Because if the malware actually miss the authentication phase, right? So then this malware will not get a chance to learn that shell ID. So in this case, then the malware again doesn't know how to provide a valid shell ID. So then it will not work either. Okay, so basically I'm talking about this, right? So the shell ID is only generated by the server and then sent back to the client during the authentication phase, right? So if the ShadowMove malware is launched later than that, right? So later, that is already after this legitimate authentication, then the ShadowMove will not have a chance to learn this shell ID later. Okay. So that's what I'm talking about. And then the third limitation is that the current design of the ShadowMove for the Linux we have to still rely on a small amount of code injection. So that's because the Linux implementation for the socket sharing is different from the Windows implementation. Okay, so I think to wrap up, so we basically discover this ShadowMove strategy that allows the APT attackers, right, to make the very stealthy lateral movement within the target compromised network. So it leverages existing and benign network connections to work. So it doesn't require any elevated privilege, any new connection, extra authentication, or code process injection. So we developed a prototype for the latest version of Windows and Ubuntu Linux, and then which can successfully abuse 3 common protocols, including the FTP, the Microsoft SQL, and the WinRM. And then we also experimentally confirmed that our prototypes they can evade the detection of many modern state-of-the-art defense mechanisms. I want to thank my co-authors, in this project. Professor Bill Chu is my colleague in the UC Charlotte, and Qingyao Wang is a faculty member in Louisiana State University. So Amir was the student working with us. Now he graduated. He joined Microsoft now. And also MD Rabi Alam is still working on his PhD dissertation right now. So with that, I want to wrap up the talk, and then I'm ready for your questions.
Thank you, Dr. Wei, for sharing that with us today. And if you guys have any questions, you can either drop them in the chat or unmute.
Oh, I saw a question. What is the main difference to the session hijacking? The difference? That's a great question. The difference is that this is done on a host level. So I think the session hijacking I mean, from my knowledge, the session hijacking. I mean, you are talking. Normally, is that this is done from the network. That's my understanding. Okay. So if my understanding is wrong, please just say and correct me. Okay. So, but in our case, we are doing this from on a host. So basically, we will, we will try to duplicate a socket associated with a session, and then we abuse this socket to inject the malicious traffic in the existing session. So this is my understanding of the difference.
Yeah, excuse me, I have a question, please.
Yes, please.
Yeah, according to, please correct me if I'm mistaken, according to my understanding of the session hijacking, because I was about to ask the same question.
Mm-hmm.
Session hijacking, the attacker is waiting until there is a connection established between the client and the server. Then the attacker will like send a reset packet or try to close the connection with the client, and then will connect with the server as if he's a client. Is that like the same scheme that you are using in your attack?
No, so the session hijacking is done over the network level. So basically, for example, on a public Wi-Fi, right? So then the attacker will just utilize the public media and then to inject the additional packet into the stream. So that's the how the session hijacking is done. But we don't use that idea. So instead, our attack is on the host, as I said, on one of the endpoints of the connection. So in this side, for example, right? So the session hijacking would be doing something like, I don't know, yeah, you can see my arrow, my mouse, right? So maybe actually inject somewhere on the network, right? And so it happens at the network level. But in our case, our attack happens on a host, So this on this host, then we get the duplicated socket, and then this is still on a host. So then we use the socket on the host to inject the packet into the connection. So basically, this is a different attack method.
Okay, thank you.
You're welcome.
Do we have any more questions for Dr. Wei?
So I'm sorry, Z. And so in order to be successful for this shadow move, and victim machine needs to be compromised because you are in the victim machine and try to do some footlow and try to monitor the network and to see, is that right? The victim machine is already compromised in some way.
Yes. So yeah, that is assumption.
I see. So in that sense, yes, and the user does not need it to be elevated. But why not, since the machine is already compromised, why not do something directly? Just say impersonate the machine, say doing something. I'm sorry, I'm new to this part. I think this is a great idea, but I just thought of like intuitively, since this machine is already compromised, why not do? Yeah, go ahead. You know what I mean? I try to direct it, say make an FTP connection, doing Win remote, and that kind of action. Is that possible?
So yeah, that's a great question and a great observation. So basically, you are saying that then how can we? Why not we prevent attacks? At all, right? So yeah, if we can prevent all attacks, then of course then this ShadowMove will not have a starting point. But the reality today is that that's not impossible to prevent any attacks, right, on our computers. So yeah, because we have spear phishing and all these well-known techniques that will let the attacker somehow break into a computer, right? So
Yeah.
so once that happens, then ShadowMove has a starting point. And also the second, I guess your idea was, how about we just get some directly make a connection to a target FTP server and then try to log into it and then and then
yes, yeah,
yeah,
that's kind of naive, yeah.
Yeah, but then yeah, we know there's authentication as a protection, right? So every server has an authentication to prevent any unauthorized user to just randomly jump in and then do abuse, right? That's why we have authentication. So there is a password, user password. There's a two-factor authentication and so on. So yeah.
Thank you.
You're welcome.
We got a couple questions in the chat.
Yeah.
What do you think the best defense for this attack, assuming the threat model is accurate?
Yeah, that's a great question. So the best defense, I think, what we are, I think is that we need to, first, we need to make sure, for example, do a better design at the host level, try to, let's say, eliminate the socket duplication kind of scenario. Okay, if that can be done, right? How to put more control over the socket sharing. I just have a wild idea, but I don't know exactly how to do it right? Because we have to still support the existing applications that needs to duplicate the socket and so on. And then this is one wild idea, that is how try to improve the design of the operating system in terms of the socket sharing. Okay. And then one idea. Then the other less ideal idea is try to do a detection, right? If we cannot prevent this thing from happening, then we can do a better detection. So, but this detection has to be kind of a more holistic. So we have to collect information from multiple nodes, right? That is involved in this process, and then try to see some traffic patterns, and then see if there's some suspicious. Because in this case, it's not about a suspicious connection, right? Because all the connections are actually legitimate. They are all benign connections. So only look at the connections is not enough for the detection. So we have to actually look into the request payload, right? So for example, normally what kind of commands will be sent over the FTP, that connection, and then because the malware, needs to do something special things like remote execution and so on. So then we may see some different pattern in terms of the actual commands inside those protocols. So hopefully we can first somehow build a profile of what kind of commands are used under each protocol, and then build a normal profiles, and then later try to detect whether there's any deviation from that normal profile. And also another idea is to combine the network level detection and the host level detection, right? Because this ShadowMove requires the host level socket duplication plus the traffic injection. So if we can do a network level anomaly detection, and then we identify some host that seems to be sending some suspicious traffic, and then we also look at inside the host and see if that host, any process has done something about the socket sharing, socket duplication. So then combine these two, maybe we can have a more effective detection. Did I answer your question?
All right, last call for questions, anybody? And then we're gonna go ahead and take a short break before our next talk. All right, Dr. Wei, I just want to thank you again for giving this presentation. It was very informative.
It's my pleasure, to give a talk in the CAE forum. Thank you very much for the wonderful questions and for your participation.